Hello, everyone, and welcome to this talk about Deletion Framework, which is how Facebook upholds its commitments towards user data deletion. My name is Benoit Retz. I've been working at Facebook for 6 years and in deletion for the last 4 years, both as an engineer and as an engineering manager. Quick introduction. Deletion Framework is basically the framework responsible for deleting user data at Facebook. So imagine if someone wants to delete their account, we need to identify what is the logical subgraph that represents all of their data. That data is going to be spread across millions of machines, dozens of data stores, and we need to make sure that everything is deleted. We handle approximately 20 billion graph deletions per day, which accounts for 500 billion individual objects deleted again per day. Finally, this talk is going to be a bird's eye view of many systems that make Deletion Framework rather than a deep dive in any. This is going to be the outline of this talk. We're going to see a design overview, the guarantees that we provide, how we monitor those guarantees, which is quite important in the world of privacy, and a quick conclusion towards the end. Without further ado, let's get started. Deletion Framework design overview. First of all, the data definition language. A key learning we had very early in the life of this team was that we cannot expect people to write their own deletion logic. Like if we ask people to use some data definition language to define how their data is going to look like, we cannot expect them to write the logic to delete that data because first, most of the time, they're not going to really understand how to do this properly. They're going to write bug in the deletion logic, which is because you want to be very reliable. And also like the deletion logic and the data definition are just going to drift apart over time. So basically, we moved to generating the deletion logic from the data definition. And to do this, we have multiple annotations that people can put on their schema. One of them is the storage configuration. So where is that data stored? The other one is the deletion edges annotation. So basically, how do we work the graph? And then finally, deletion constraints, which is a way we give developers to protect their data from erroneous deletions. Here's an example. We have 3 schemas: user, post, and comments. And in this example, there is a deep edge from user to post, the from user to post edge. A deep edge is basically an edge that when you encounter it, you delete the edge, but traverse it first and delete what's on the other side recursively. So in this case, we would call the post deleter, delete the post, and again, this post has a deep edge toward comments. The opposite of this is the soaks from comments to post, for instance, are here annotated shallow in the schema. And what this means is when you delete the object, you would delete the association without actually traversing it. So you would delete the comment, but not the post. Here we have constraints put on those schemas, all examples. On user, the constraint is never deep deleted. This is a constraint we use, for instance, when we never want the object type to be deleted as part of another object's deletion. So you wouldn't be able, if you have this constraint, to like start a page deletion that would then cascade down to deleting users. And that's a safeguard we have in place to prevent erroneous deletions. And basically, once we take all of this, we generate some code and we generate deleters. Deleters are classes that are basically responsible for working the graph. And there's 2 types of deleters. There's the primitive deleters, which is deleters that the Deletion Framework team writes manually. Those are the ones that are actually responsible for doing the deletes. So they are basically the interface points with data stores that hold the data. And the other deleters that are generated never do any delete. They just delegate that to other generated deleters that would then in turn delegate that to the primitive deleters. So in our example here, the user deleter would delegate the self deletion to the storage deleter that would delete the object and the associations, follow the deep soak, and then call the post deleter that is also generated. Let's go over how we work the graph in Deletion Framework. We use the DFS mainly because it's the simplest algorithm to implement. And basically, we need to be reentrant, meaning that if our process gets killed in the middle of its run, we need to be able to restart without having lost any data, right? And having everything still accessible to prevent orphan data from happening. And we need at least 1 semantics. Let's take an example graph to see how this happens. So here we have a deletion request on the post. And basically what the framework is going to do is first read the object, checkpoint it on the stack. The persistent stack here is basically what allows us to do our DFS, and this is also what allows us to restart a deletion. So when the deletion is restarted in our execution layer, we can just read what's on the stack, reinstantiate all of the deleters that we haven't completed yet, and then keep the deletion going. We log restoration logs before any delete that we do. Restoration logs are used for disaster recovery. And yeah, we basically make sure that we're able to recover graphs that we delete. After that, we do the self-deletion and then the graph deletion. The graph deletion is basically going to be reading all of the SOCs and then looking at the deletion behavior on the SOC. So here we read the SOC, which is looking at the author of that post. This is a shallow SOC because you never want to delete the author of post when you delete the post. And again, log restoration logs, delete. And then we move on to the other types of SOCs. These ones are actually deep because you want to delete the comments as well as the post. So read the comment, checkpoint on the stack to be able to be reentrant, log restoration logs, delete, do the graph delete for this object recursively because we call the deleter, which is responsible for this. Once the deleter is on executing, we pop it from the stack, and then we basically go back up, delete the SOCs, and move on. And we keep this process of doing a depth first search and delete the data as we go back up and pop objects from the stack once they're done. Here, we reach the point where the post deleter is done executing. So we pop it from the stack and we are officially done. We deleted a graph. As you've seen, in this example, there is a lot of round trips, which is why we've implemented batching, which is basically a way for us to iterate over the graph faster. The way batching works is all of those actions that we've seen before, so read, checkpointing, logging restoration logs, and actually doing the writes to data store are going to be done in batches, right? So first of all, the framework is going to read a lot of the data until we reach a threshold that is either there's too many objects that we keep track of, or it's just too much to handle in terms of memory, and we need to flush this. And when that flush begins, the first thing that happens is we checkpoint things on the stack. We add all of the objects that we're going to delete because we don't have atomicity on the rest that we're going to do after that. So we might have some parts of the graph that get deleted, some of the graph that doesn't. And if we weren't going to persist everything on the stack, we might have parts of the graph which are then not accessible if we were to try to traverse that again from the top. We then log to restoration logs. Here we batch everything together, so it's only one write. Then we do all of the delete at once, pop things from the stack that successfully were deleted and finished their graph deletion. Here there's only one of the comments. And then we basically move on, do the same, and delete all of the graph. And this is what allows us to go much, much faster. Let's take a look now at how we can schedule deletions in the future. So scheduling deletions in the future, it's essential to enable ephemerality at Facebook. So think Instagram stories, for instance. Those are pieces of content you create, but they have a time to live. And after that, you expect them to be deleted. Another example would be the account grace period. So whenever you want to delete your account, there's a 30-day window during which you can basically log back into your account. And this is powered by this piece of infrastructure I'm going to present. It supports scheduling deletions years in the future. This is useful for financial data, for instance, that we need to retain for some amount of years. Supports some custom TTL logic, so you can evaluate whatever logic you want at deletion time to make sure that you want to delete. And that allows us to do things like deleting a post 9 days after the last comment, for instance. And this processes 160 billion events per day. And basically, the way it works, I'm not going to go in too much detail, but at creation of the object, we basically log something which is then going to be aggregated by a pipeline. And 2 to 3 days before the actual expected deletion time, those get scheduled for deletion to our execution layer. And that execution layer is then going to wait until the exact time for the deletion and then evaluate whatever logic the product team might have put in place. Based on that, they're going to take a decision, which is going to be either we delete the object, we cancel the deletion, or we just postpone it some other time in the future. And that's how basically we allow those custom TTLs from being in place. Let's move on to the guarantees that we have that we provide by the framework. First of all, the scheduling is quite important. It happens like deletions are in two distinct phases: the sync part, which runs synchronously in the web request, and the async part, which is basically responsible for deleting the entire graph. If you delete very large graphs, for instance, a page of someone very famous, there is no way this is going to fit in the deletion request, which is why we have those two separate processes. In our example that we saw earlier, the sync part here would only be responsible for deleting the top level object, which here is the post. And basically, the sync part is responsible for hiding the rest of the subgraph. And how does this work is when the post is deleted, all of the other objects in the graphs have what we call privacy policies, which is basically a way to evaluate if someone has a right to see some content or not. And this is something provided by the definition language we saw earlier. And in our example, on comments, there is a rule that says this user can see this comment only if the user can also see the parent post, right? And in our case, the post is deleted. There is no way the user can see that post. Therefore, everything else is invalidated at read time. The main issue we have with this is the privacy layer is actually distinct from the deletion graph. So we cannot statically enforce that everything is going to be hidden properly when we delete the top level objects. So the way we make sure that this happens is whenever we actually run the deletion, we have checks in place where we try to load the objects and try to assess whether the user can actually read the data or not. For everything that can be loaded, we then escalate that to someone in the company to actually fix their privacy policy so that whenever we delete the top level object, everything gets hidden properly. Eventual completion is another very strong guarantee that we provide on the framework. And basically the problem we're trying to fix here is deletions, when they run, they are going to encounter infrastructure issues. Some data store might be down, there might be some bug in the code, or they might just be dropped by dependencies when you expect them to be executed to their completion. Or they might fail halfway through their scheduling, so the deletion started but wasn't scheduled to like our execution layer. But basically, every deletion that gets started on Facebook needs to eventually complete, right? And the way we guarantee this is every execution of a deletion actually logs some events in some table somewhere. So they log when they start getting executed, the exceptions they encounter, the amount of runs that they do, and whether or not they complete. And all of that data is then aggregated into something that computes a status for all of the deletions that are in flight, right? And this is going to keep track of the deletion until we see a completion log, which basically means we deleted all of the data. And from that, we extract two sets of data. The first one is the idle deletion, which are deletions that don't get executed because they've been dropped by some dependency somewhere. And those get rescheduled. And then the other set is a set of what we call stuck deletions, which are jobs which encounter persistent infrastructure issues that need to be escalated to people in the company, right? So imagine someone writes some deletion logic which doesn't handle some corner cases properly. Those deletions are never going to make progress, right? And to make sure we actually go through, we need the person to actually fix their code. And this is why we have that monitoring in place and that escalation process. The other guarantee we have is eventual completeness, which basically means that everything is going to be deleted. We're not going to leave any data behind. And we have multiple issues that can lead to orphan data, right? So you can have bugs in the deletion logic. You can have race conditions where some processes somewhere raise data that refers to the data you're trying to delete right now, and those processes don't have knowledge of each other. Or you can have like misconfiguration of deletion settings that might lead to orphan data, right? And we need to make sure that everything is cleaned up retroactively. And the solution we have for this is object-free deletion. And so for that, we basically look at all of the objects that have been deleted, and we look for edges that originate from objects that don't exist anymore, right? So we basically have the IDs of objects that existed in the past, but that don't exist anymore. And we look for all of those ASOCs that originate from those. Those ASOCs are called dangling ASOCs. And basically when we find those, we basically reapply the deletion logic that's associated to them. So here we have a post and a comment, which is div. So we delete the side of the graph if it exists. And then if the ASOC is shallow, we just basically delete the ASOC. We run migrations on every object type. The migrations start every other week, and they basically iterate over all of the data that Facebook's own, and then schedule deletion for like whatever data needs to be deleted retroactively. Finally, another very important guarantee is restorations Data losses are inevitable when we operate a system at the scale that we do. They can come from product bugs or deletion misconfiguration. And this is why basically we log restoration logs before any delete we issue. And those are different from your typical database backup, because database backups allow you to like go back in the past to a snapshot. Here, those are graphs indexed. So we can restore an entire subgraph individually from the rest. And that allows us to basically really filter exactly what we want to restore. The way they work is, as you've seen, when deletions get executed, they write some data to a write-ahead log, which is then aggregated by a tailor into like bigger payloads and returned to some data store somewhere. An interesting issue we had to deal with is where we need to have an upper bound on how long we can retain deleted data. And here we reach an issue where we store that data, they might have backups over backups, right? And to counteract this, what we had to set in place is we added an encryption service which provides a daily rotating encryption key. And all of the restoration logs of a given day are encrypted with that key. And when that key expires, this basically means the data is effectively deleted. And that's how we enforce a very strict upper bound on how long we can retain those restoration logs, no matter which storage we are storing our data on, and whatever backups policy they might have. The ways to prevent data loss, none of them are foolproof, but they have some good success rate. The first one is do static analysis on the deletion graph. So I've explained we have deletion constraints, and we can check like if they are violated, and if they are, we just prevent the code from being pushed in the first place. Then we have dynamic checks, which at runtime evaluate if the constraints are actually respected or not. And finally, we run some predictions on the edge's deletion behaviors. So by looking at by looking at the data, we can predict if it's going to be likely a shallow soak or likely a deeper soak, and you can try to find mistakes that developers do early on. Monitoring guarantees is a very important part of what we do. And those are just examples of things that we monitor. So for instance, for scheduling, we look at how many objects are still visible when a deletion is running, so that we can try to understand how much falls through the gaps. For eventual completion, we look at the amount of deletions that get rescheduled, the amount of deletions that don't get executed for more than a day. Eventual completeness would be like the amount of objects we redelete. Restorations, what is the oldest encryption key that we store. And one of the concepts that's very important with the guarantees that we provide in the world of privacy is we always have like a happy path, which is how the system should behave if everything goes well, right? And then we measure the happy path reliability. And then there is a lot of things that are going to fall through the gaps, right? And we measure what is the amount of things that fall through the gap. And then we have those safety nets in place, which are the redeletions, for instance. And then we measure how many of those safety nets, the reliability of those safety nets themselves. So we have basically like multiple stages of monitoring, which is how we basically ensure that we do respect our commitments towards user data privacy. Bonus points if you can have a completely orthogonal way to measure the success of what you're trying to do, which isn't tied down to your framework, right? It's often hard to do, but when you do, you have like a much stronger confidence in what you're doing. And then another bonus point would be like having a second level of safety net. So like no safety net is going to be foolproof, right? And a second level can definitely go a long way. In conclusion, deletion is a hard problem. The happy path when you deal with privacy and user data in general is not enough. You always need to have those safety nets in place for things to automatically mitigate whatever failure you're gonna have when you like operate a system of that scale, right? And finally, for deletion and privacy in general, we need to make it easier for developer to do the right thing than to do the wrong things. And it's the same also with security, right? We cannot expect every product developer to understand security to a point that they will never write any code that has vulnerability, but we need to embed security and privacy at the infrastructure layer so that by default, when people use tools that we provide, they are going to build products which are privacy aware. Thank you very much. I'd like to thank everybody who's working on building Deletion Framework and making sure that Facebook deletes user data. This is definitely a very hard problem, and I'm very much impressed by the amount of progress we've done in the last 4 years that I was there. For any follow-up questions that you might have, this is my email address, and I'll do my best to answer them all. Thank you very much. Bye-bye.